Hello, everyone. Thanks very much for coming today. It's a great pleasure today to have Dmitri Kavetski with us here from Australia. Actually, I've known him for 15 years or so. I'm going to give you a brief overview of what I know about him and his history a bit. He finished PhD back in 2005 at the University of Newcastle with George Kuzira. And then he had multiple appointments here and there, including a postdoctoral position at the Princeton University before he joined the University of Adelaide in the civil engineering department as a full professor, which was quite impressive, someone out of PhD and postdoc to be appointed as a full professor at the beginning. So he's been there since then, and just recently he has been appointed as the deputy head of the School of Civil, Mining, and Environmental Engineering, I would guess. So he has been a thought leader in the area that I'm also working on, uncertainty analysis. And I remember learning about these things by reading his papers. And I think he published a seminal paper back in 2003 or 4 on Bayesian inference in the area of uncertainty analysis for parameter inference in a way that you can have a good characterization of predictive uncertainty, and bringing input uncertainty into play, including errors in precipitation and how you can characterize that, come up with a parameterization to describe those errors, and bring those into the uncertainty analysis framework. And he developed a method called BATI, which stands for Bayesian total error analysis. So since then, he's been a thought leader. He's published some other seminal papers that I liked very much, like smoothing strategies to have a better performance or behavior of the hydrologic models, typically at the catchment scale. So I'm very happy to have him here, and thanks very much to Martin Clark for hosting him and bringing him here. So without any further ado, I'll pass the floor to Dmitri. Thanks very much.
Thanks, Saman, for that introduction, and thank you very much, Martin, for inviting me to Saskatoon. I meant to be here a while ago, but finally a good excuse. So what I'd like to share today is some of the recent work that my colleagues and myself have been doing at the University of Adelaide in Australia on the topic of probabilistic streamflow prediction. So I don't have to introduce too much the water cycle. All of you are hydrologists in one way or another. But the scale that I'm going to be primarily concentrating is the catchment scale. Certainly, there's been a lot of exciting work at the hill slope scale and also at the continental scale. But most of our interest at this point has been as a research group at the catchment level. And in this context, I like to distinguish a little bit between what I call engineering hydrology and scientific hydrology. Of course, there's a lot of synergy between these broad directions in hydrology, but as an engineer, I'm interested in making practical predictions. As a scientist, I'm interested in deeper understanding of why we get the results that we get, how can we improve them. Regardless of which aspect or which perspective you take, and I think there are legitimate interests in all of these perspectives, there have been many, many different types of models used to describe the water cycle dynamics, distributed, lumped, conceptual or physically based. Again, regardless of the perspectives that you take here, I think some of these ideas that I'll present might be of interest to you, and I'm hoping they will be. These models are increasingly used in different aspects of environmental management and decision making. I think that trend will only continue into the future, and we're interested in producing credible predictions. All right, so it's not enough to produce just one number. We have to characterize the uncertainty in that number, but also make sure that that number doesn't stray too much from what actually happens in the future. And this is an example of a project of practical hydrology, the seasonal streamflow forecast by the Australian Bureau of Meteorology. Here we're interested in producing streamflow forecasts 1 to 3 months ahead. And these forecasts are used by water managers across Australia to inform their various decisions, for example, dam operations and so forth. The service itself has been operational for a few years based on the statistical forecasting system, and myself and my research colleagues in Adelaide have been collaborating with the Bureau on the topic of dynamic streamflow forecasting. And again, the objectives here are to provide high quality streamflow predictions across the entire continent. So that provides a bit of a connection between the catchment scale and the larger scales. So what I want to do today is to give a bit of a broad overview. I'm not going to necessarily go into a lot of technical detail, but I'll give you a bit of a flavor of different research directions that I've been exploring with many colleagues. And I'll sort of classify them a little bit into probabilistic streamflow prediction, where I'll talk a bit about the concept and motivation for that. And also I'll talk about hydrological model development, something that I think many of you are involved in. And in particular, I want to talk a bit about how to use flexible models to improve spatial predictions. I'll briefly touch on some other developments if time allows, otherwise I might skip them, but I will be around tomorrow, the rest of today and tomorrow, and so if you have questions, I certainly would be very interested in having a talk with you. Okay, so regardless of whether we're looking at real-time prediction or seasonal forecasting, we're looking at a number of attributes that our forecasts should satisfy. And probably one of the most obvious ones is the precision of the prediction. If we are producing a forecast with plus or minus 10% error, intuitively we expect that to be a better forecast than one with plus or minus 50% error. Okay, that's a fairly intuitive concept. To achieve this, we need to represent the catchment processes accurately in our models, as well as extract as much information as possible from the data that we have available. But precision on its own is not sufficient. If we estimate plus or minus 10% errors, but when the time comes, we take measurement of the actual flow and the error was 50%, well, the first time that happens, I think people will accept it since there is an inherent uncertainty. But if this happens over and over again, what this indicates is that we have a misleading forecast. We are saying that we have plus or minus 10% uncertainty, but in reality, we routinely get 50% errors. That's not a very satisfactory situation. If we keep making this kind of predictions, then people are going to lose confidence in our forecasts. And this aspect is a little bit less appreciated, perhaps, and is referred to by statisticians as the reliability of a forecast, of a probabilistic forecast. And statisticians have been predominantly interested in precision and reliability, but as an engineer, I'm also interested in practicality. If it takes forever to calculate or compute a forecast, then that's not a very practically useful tool. Now, regardless of whether we are looking at real-time or longer-term forecasting, obviously there's going to be a number of sources of uncertainty which are going to be affecting our predictions. And here I've collected a couple of examples which I think are particularly sobering. The first one is an illustration of data uncertainty. Here is the eastern coast of Australia a few years ago, and you can see the outline of the coast here roughly. The crosses represent rain gauges. Okay, so you can see that we have a rain gauge measurement network, and it's generally quite okay in many instances, but it's also patchy in other cases. So for example, if we look at this catchment here, the Bigara catchment, it's not a small catchment necessarily, it's about 1,200 square kilometers, but it doesn't have a single rain gauge in it. And if we look back at the record in 2009, nearly 10 years ago now, we can see that there's been this storm event, which in fact was nicely centered on that catchment, but it largely missed all the rain gauges around it. All right, so if we are looking at making predictions at that particular catchment, but we only have the data from the rain gauges, then we can see that we would be in trouble. Right, we'll be missing most of the forcing. Okay, so this sort of schematics have motivated a lot of interest in rainfall uncertainty. But that's certainly not the only source of uncertainty that we face as hydrologists. Models are obviously a major simplification of the real environment, and I think there is a lot of recognition that if you build a model for a particular humid environment, it might not necessarily perform the best for an alpine environment or even for an arid under arid conditions. Okay, and so again, how do we build models that can accommodate the whole range of environmental behavior is something that has concerned hydrologists for quite a long time. Martin has done a lot of work on this, and I've also been interested in that aspect. Okay, I think it's fair to say that we've had relatively little success so far in building these types of models that work well everywhere. Okay, so why use probabilistic predictions in these circumstances? Well, I'm hoping to provide a bit of motivation in the next few slides. And suppose you're a manager that has to make a choice between action A and action B. Let's say that you've done some modeling and it tells you that action B is likely to produce this outcome. Here on the horizontal scale, I have the improved system performance. For example, might be the stream health or drought resilience, right? Whereas action A produces an outcome that falls somewhere here. And let's say we also have some performance failure below around this region here. Okay, if you are only given this piece of information, then most of us, I hope, will choose action B because it leads to a better outcome. But this is only a part of the picture, right? What if we've undertaken some uncertainty analysis and it turned out that action B, even though on average produces a better outcome, but it's also subject to increased uncertainty. Okay, whereas action A on average produces a worse outcome, but there is less uncertainty in it. All right, so all of a sudden now we have a more complex decision on our hands. But on the other hand, we also are more informed. So if we are risk averse, we might choose to take action A. Right? It really depends ultimately on what this performance failure means. Does it mean a flooded sidewalk or something much more substantial? And so again, having some idea of the uncertainty in these predictions can really help us make a more informed decision. Okay, so this is one of the motivations that that I have in probabilistic predictions. Try to describe the uncertainty in future outcomes as well as in any other quantity of interest. Looking solely at uncertainty as a given is probably a somewhat passive perspective. I think as scientists we're also interested in reducing, in understanding where the uncertainty actually comes from and also reducing that uncertainty. And so, again, I will not talk too much about that today, but again, if you're interested, I'm happy to chat with you about that separately. Certainly there have been many studies of where the uncertainty comes from in hydrology, and the reality is it comes at pretty much every step of the modeling process. We see uncertainty coming in our inputs. For example, we are measuring the rainfall of the entire catchment, which might be thousands of square kilometers, using solely information from a few rain gauges in many cases. At the other end of our models, with Streamflow, we are using, in many cases, rating curves. And again, this is maybe a ballpark figure of accuracy, 10 to 20%. But certainly during larger storm events, we expect to see deterioration in the accuracy. The first and the last boxes represent data uncertainty, but of course we have the model in between. And so if we are trying to represent a real catchment with all the heterogeneity using just a few simplified buckets, then obviously we're going to also be incurring a lot of simplification in that respect also. Okay, so how do we deal with all this uncertainty? Probability theory provides one technique to do that, and the idea here is that we're going to be using probability distributions to describe the uncertainties in different variables of interest to us. This is one of the particular equations of probability theory called Bayes' equation. Many of you would have seen it before, introduced by Reverend Tom Bayes more than 200 years ago. Superficially looks probably one of the most simplest equations you will see, but in fact, if you have tried applying it in practice, you will see that there is a lot of subtlety in how do we specify each of these different terms here. The likelihood function, our priors, a lot of thought has to be put into them so that we get something reasonable as the outcome. But the idea itself is quite intuitive. We use probability distributions to describe the uncertainty in the quantities of interest, and then we are hoping, I should say, that the information in the data can help us refine that knowledge. So here, if we're looking at a model parameter theta, we start with an initially vague idea of that parameter, and then the data comes in, and hopefully we're going to see a constraint on our knowledge. We're going to see an improvement, a refinement. You can see this relates a little bit to the precision attribute that I talked about earlier on. Here we have something that is quite imprecise, whereas on the right we have refined our knowledge. Okay, so in the past I have worked quite a bit with fairly complex Bayesian setups. Here I want to share some simpler ideas that are more suitable for operational applications. And a lot of these operational applications revolve around characterizing the uncertainty in the streamflow, right, in a variable that's of interest to us. And if we decide to use a residual error model, in other words, we are looking at a difference between the observed and predicted values, we will see that our errors are firstly heteroscedastic. It's a statistical term which refers to the larger errors occurring for larger flow events. And secondly, the errors are persistent. So we don't just get random errors, but rather we often have a sequence of large negative errors or large positive errors. Okay, and so these two characteristics have to be reflected in our uncertainty models if we want to capture that uncertainty in a reliable way. And the classic strategy here is simply to say that all of those distinct sources of uncertainty, the rainfall, the model, the stream flow, are captured in this single epsilon term. Okay, and again, if we look at some of the basic statistical textbooks, they will tell us that we could model them as Gaussian with a constant variance. Obviously, a simplified assumption. If we apply that assumption, we find that our prediction limits tend not to look very reasonable. Okay, in this particular case, we can see that the uncertainty in the low flows seems to be overestimated. We can see how wide those limits are, whereas we are still missing quite a lot of the high flows. So this is just a very simple motivation that this assumption of Gaussian constant error, constant variance errors is just not very suitable in hydrology. Now, if we relax that assumption in a very simple way, and we say that our standard deviation of the errors depends on the flow, in other words, we provide a mathematical mechanism to say that larger flows will have larger errors, then we get something that looks more reasonable. Okay, here we can see how much we've reduced the uncertainty in the low flows. Okay, and in fact we are still retaining, or in fact we've expanded a bit the uncertainty in the high flows. So this provides a more useful prediction because it's more precise for these low flows and reflects the larger uncertainty in the high flows. But this is obviously a very simplistic model still. Okay, and so when the Bureau has approached us to help them develop their operational forecasting system, we wanted to look at a range of residual error approaches and also look at different performance metrics. So we have more confidence in the results that we have. And so in this study, we compared 8 different residual error models based on different transformations. For example, the logarithmic transformation, the Box-Cox transformations. And we applied those techniques over 23 catchments in Australia and the US. So that included catchments in arid regions and humid regions, as well as the MOPEX dataset for those of you who are familiar with that. And we've used 2 hydrological models, GR4J and HBV. They're both lumped conceptual models that are applied at the catchment scale. We looked at a number of performance metrics, which I'll cover in a second, but this was a fairly lengthy exercise. Took around 3,500 calibrations and over 4,000 CPU hours because we were doing cross-validation. Okay. Again, I don't want to go into too much into the techniques, into the technical details, but we've compared 2 broad approaches for the residual error models. The first one is what we refer to as a direct approach, where we are focusing our attention on how to express the standard deviation of the errors. Okay, for example, we could say that the standard deviation is proportional to the flow rate, and these types of approaches we refer to as being the direct approaches. A simple example is the weighted least squares approach. On the other side of this slide, I have transformational approaches, which are used based on a slightly different principle. They are based on using transformations of the flow before calculating the residuals. Okay, but once we've applied these standardization or the transformation, we still make that ubiquitous Gaussian assumption. It looks superficially quite different, and in fact there are some differences, but there are also some similarities. If we start to look at the shape of these residuals, of the predictions, they are often fairly similar, except that with transformations it's a little bit easier to achieve this skew in our predictions. You can look at the details of the theory in this publication. I will move on to some of the metrics that we use to assess the predictions. But the first one is the reliability. In other words, are we consistent with observed data in a statistical distribution sense? The second criterion was the precision. We wanted to have as little uncertainty as possible in the predictions, as long as we're being still reliable. And as hydrologists, we're also interested in the longer-term biases in these predictions. Are we matching the long-term bias? Are we matching the long-term volume, the long-term observed volume by the model? Here I just want to illustrate these ideas because these 3 criteria can be a little bit confusing if you haven't seen them before. But here is a perfectly reliable prediction. Okay, this is climatology. So all I've done here is I've plotted the empirical distribution and then the observed data. Okay, and you can see that, in fact, these uncertainty bands capture the correct proportions of the observed data. So technically speaking, we're reliable. But if we look more carefully, we can see that there is a huge amount of uncertainty in these predictions. And if you are a decision maker, I would say that this kind of forecast would probably be pretty of questionable value to you. Okay, it's just too vague, too broad to be useful. Here we have the other extreme. we have a situation where our predictions are very precise. Okay, the width of these uncertainty limits is very narrow, but they're not very reliable. We're missing the majority of the data. And so again, it's a misleading forecast, not a very satisfactory situation. We can also have biases where we have a systematic shift in the model predictions compared to the data. So quite a few different patterns in which things can go wrong. Ideally, we would like to see something similar to this top panel, where we have reliable predictions that capture the observed data quite well, but they also are fairly precise, so that we actually get something useful from the forecast. And so if we now start to look at the model predictions, we separate catchments into two categories. The first one is the perennial catchments, where we have flows at every day of the year, and we also have ephemeral catchments where flows stop over certain periods. And we found that in these perennial catchments, here is an illustration from the Spring River in the US, the logarithmic transformation model performed among the best. It provided reliable predictions as well as quite precise ones. Here is a contrast to what happens with a standard least squares model, which was far from well performing in this case. And we can see how it overestimates the uncertainty in the low flows and underestimates them in the high flows. Okay, so what we're finding in this case is that the logarithmic model performed really well in these perennial catchments. In ephemeral catchments, we saw a different picture. Here we actually found that the Box-Cox transformation with a lambda of around 0.2 outperformed the logarithmic transform. And we have a bit of theory to explain this. It relates to the way the log behaves for near zero flows. Again, it's nice to not just look at the empirical results, but relate them to theory. And if you're interested, we provide some explanations here. Okay, we're already seeing then that for different catchments, we need different residual error models. But it's actually a little bit more complex than that, and we also have trade-offs between different performance metrics. For example, in perennial catchments, if we look at our three performance criteria, reliability, precision, and bias, different residual error models are better at achieving one or the other of these performance metrics. So we have trade-offs, not just across different catchment types, but also with respect to different performance metrics. Okay, so we can't always get everything that we need in our predictions at this point. And these trade-offs are also visible for ephemeral catchments. So for example, here being close to the center is the best, and so this Box-Cox model with parameter 0.2, lambda of 0.2, is better for reliability, but has worse precision. Okay, so again, I think quite an interesting and an important aspect. If you're making a choice of these models, you need to think of some of your objectives, and hopefully these kinds of trade-off analysis can then guide your choice of error model. So how does this translate then to the predictions by the Bureau of Meteorology? Well, as I've mentioned, the Bureau is undertaking forecasts at hundreds of catchments around Australia, and the benchmark that was used in this study was effectively a very simple residual error model that was used by the Bureau prior to this project commencing, and in many cases we saw very poor precision from that model. It was actually worse than climatology. And after we've implemented the recommendations based on that analysis, on that study that I've described, we are seeing an improvement in the precision. This is predicting 1 to 3 months ahead. And what is really, I think, encouraging from our perspective is the improvements across the continent. So here is the previous approach. We these sites are color-coded according to their performance, the number of months where the model is performing better than climatology. We can see that with the original system, the performance was quite patchy. There were some cases where in every month of the year, the model was inferior to climatology. So it looked sort of fairly uniformly distributed in quality. Whereas once we've implemented that, the model, the Box-Cox transform model, based on those empirical case study results, we're finding now that the majority of the catchments are now outperforming, the model is outperforming climatology in the majority of the catchments. So again, not a terribly high bar, climatology, but it's in fact an improvement over what we had before there. Okay, so the number of sites where we've achieved, where the model achieves high forecast skill increased from 20% of the sites around Australia to more than 80%. I think this was a really interesting project from our perspective because it was an example of collaboration between academics and a government agency, and certainly we learned a lot of things as part of that project. If you're interested, there's a publication on this which describes this in more detail. What was, in addition to, I guess, the technical aspects of which models were best, what I thought was very interesting in that project is that the relatively simpler models performed better. Okay, and so I think one of the messages from this study is that if we use simple approaches in a prudent way, we are often able to achieve very valuable improvements in our predictive performance. And because they are simple, they're also feasible to implement in operational systems. Okay, so now I'd like to move on to another direction, which is the improvements in hydrological model structure developments, in particular on flexible models, on using flexible models to produce spatially distributed predictions. Again, the motivation for this comes from trying to accommodate the diversity of environmental conditions. And in fact, it was Martin who initiated a lot of these thought processes. So you might have already seen this picture from him. But this is, this gentleman is Tom Chamberlain, and already 150 years ago, so a bit less, he talked about scientists developing parental affection for their theories. So we know that every hydrologist has their own model, and I think that is some manifestation of this parental affection to some extent. And Chamberlain's idea to try to mitigate that is to try to come up is to request that scientists come up with multiple different explanations of the same phenomenon of interest, and then because we are looking at multiple alternative explanations, we are less likely to consciously or unconsciously favor one particular hypothesis. Okay, it's really the idea of looking at multiple working hypotheses, and what I'd like to talk about is how that might be applied using flexible models in hydrology. Again, the idea here is that we have multiple choices of state variables, multiple choices of processes to include, and different parameterizations. So if we're looking at a simple mass balance equation with a change in storage and then different fluxes on the right, here we might also consider different options for parameterizing the surface runoff. Okay, we might consider the VAC parameterization with a power function dependence, or for example the top model, which is based on the topographic index. The model structure here was constructed using the SUPERFLEX framework, where we are building a model structure from multiple generic elements, and each of these elements can be configured with respect to its storage-discharge relationship with different parameterizations available for different fluxes, and you can also combine multiple reservoirs in different ways. So we have already investigated this framework in the context of lumped modeling, what I want to present today is the application to spatial modeling. And we wanted to sort of approach this in a controlled way. And so we split the model development into 3 stages. The first one being the catchment discretization, the second being the model structure adjustment, and the third being the parameterization choices. So in other words, how do we split the catchment into HIUs? How do we represent the dominant processes at each HIU? And how do we constrain the parameters so we have something well behaved? The case study came from Luxembourg, where they had a densely gauged catchment called the ARTET catchment. It's a pretty small one, like most experimental basins, 300 square Ks. And one of the things that attracted us to this catchment was the diversity of streamflow patterns. If we look at the multiple sub-catchments, I think there were about 12 of them, they all exhibit markedly different streamflow dynamics. Some of them are pretty smooth, some of them exhibit double peaks, so a lot of diversity there. And I think, in fact, Jeff McDonald gave a talk on some of the double peak hydrographs in this catchment a few years ago. So it's a catchment that has received some attention in the community. The distributed model that we used here is organized in a fairly traditional way. We split the catchment into sub-catchments and HIUs, overlaid them on top of each other, and we also do routing between these elements. Nothing terribly new or exciting there, but I'll get to the interesting parts in a second. Again, we looked at the performance of the model in cross-validation, so calibrating on one set of catchments in one period and validating on a different set of catchments or sub-catchments in a different period. We also looked at not just the Nash-Sutcliffe, but also different hydrological signatures. Okay, so let's look at the first step. And here we considered 3 different discretizations. One was our null hypothesis, where our entire catchment was a single HIU. And we also looked at the topography classification into 3 HIUs and the geology-based discretization into 4 HIUs. So a fairly coarse discretization, but we wanted to see what we can do with it. And so at this stage, we're looking solely at the spatial discretization, and so we use the same model structure in each of these HIU types. Okay, once we looked at the results under cross-validation, we saw that, in fact, even though in calibration mode, everything seemed quite all right, but once we start validating on different periods and different catchments or sub-catchments, all of a sudden our uniform discretization had a pretty abysmal performance, and similarly the topographic-based discretization also was quite poorly performing in cross-validation. Okay, so that, in other words, favored the geology discretization, which maintained its performance quite enviably. This is where some of the interesting contributions came in our opinion, is in using different model structures for different HIU types. Okay, so different conceptual model structures for different parts of the catchment depending on their HIU classification. So here we're attempting to move away from the idea of trying to represent everything in a single model structure and rather use different model structures for different HIUs. For example, for the schist HIU, we use this sequential model structure with delay components. For the sandstone, we had a slightly different model structure. The alluvium was a particularly simple model structure, was represented using a particularly simple model structure. This came from some of the earlier work that we've done in that catchment, where we looked at those sub-catchments in isolation. And so here we're trying to bring them together in a single spatial model. And the motivation here overall is to try to focus on the dominant processes in each geology type and tailor the model structure to that particular process or processes. When we looked at the results, here I'm showing the performance with respect to the signatures. We found, again, some interesting results in our opinion. Again, in cross-validation mode, we find that the model with a tailored model structure is able to come closer to the observed signatures than the model with the same model structure everywhere. So here the black dashed line are the observed signatures at different gauges. The blue line is our model structure, is the model with the same structure everywhere, and the red is when we start tailoring the model structure. So we can see that both for the Baseflow index and the flashiness index, we're moving closer to these observed signatures. And this is despite the fact of having fewer parameters and, in fact, simpler model structures in each of the HIUs. The final stage of this process is to try to understand the relationship between the parameters in different HIUs. Okay, and again, something very simple that we've done here is we've looked at the model structures and we recognized that they all share some parameters. Okay, in particular this SU max parameter, which is effectively the depth of this bucket, appears in every model structure or in 3 of the 4 model structures. And so we've decided to link them together. Okay, so instead of having 3 parameters, we now have 1 SU max everywhere. And these are the parameter estimates that we've obtained previously in the 3 different geology units. There is some overlap in the values. Once we've said that it's the same parameter value everywhere, then we ended up something in the middle there. And interestingly enough, we saw no change, no discernible change in the model predictions. Right, so we've improved the parsimony of the model by removing those 2 parameters, and we see no impact under cross-validation. Okay, so it's again quite a nice result to obtain in our opinion, where we can maintain the model performance despite using a lot fewer parameters. Again, this is where we stopped in this particular study. Right, so we've looked at the discretization into HIUs, and I think the main contribution here is to look at using different tailored model structures in different HIU units. The conclusions here were that we can apply this one decision at a time approach, and for that particular catchment, under fairly rigorous cross-validation conditions in both space and time, we're looking at 10 subcatchments with quite diverse dynamics, and we're able to capture their signatures and streamflow time series quite well with 11 parameters, 7 of which are HIU specific and 4 are global across all of the HIUs. So this is, and this also gave us some insight into the dominant controls in that catchment. So in that particular location, we found the geology appears to be the controlling mechanism. And if you're interested in learning more about this, again, you can either talk to me or you can also consult the publication. So I'm not sure how much time I have at this point. Okay, so I'm just going to briefly look at a few other developments. I've talked about residual error models in the first half of the talk. Can we simplify it even further? In fact, yes. You can look at some publications where we are combining the least squares approach with the method of moments for calibrating the residual error models. Again, there's a publication that describes it in more detail. If you're interested in learning more about Bayesian inference, you can consult a book chapter where I go through the application of Bayes' theorem specifically to hydrology. Certainly there are many publications on Bayesian theory, but here I'm trying to take a fairly basic perspective and derive the fundamental equations. I've mentioned signature calibration in the second half of the talk. If you look at the hydrological literature, you can often see signatures being touted as some sort of magic bullet against uncertainty or against developing a statistical error model. In fact, there is a type of Bayesian inference referred to as ABC, or approximate Bayesian computation, which is really nicely suited to working with signatures. I've learned a lot trying to make sense of it and improve my own understanding of the theory. But in fact, what it confirmed is that it in no way bypasses probability theory. Once you are interested in probabilistic predictions, you have to be very careful with how you apply the various probability equations to describe the data. Okay, so there is no magic bullet here. Certainly promising approach, but it still requires much of the same steps that we looked at in the residual error modeling approach. I'm interested not just in looking at the streamflow, but also, for example, irrigation, and we looked at irrigation schedule models that are stochastic in space and time. So if you're interested, again, I can direct you to some recent work. And finally, I know that most hydrologists have done some kind of optimization of their parameters, and one of the current dominant algorithms is the SCE search, the Shuffle Complex Evolution search, also DDS, another widely used technique. In some recent work last year, we looked at trying to improve on those techniques. And I'll skip the next few ones. But one of the things that I find particularly promising is some of the speed-ups that we're seeing when applying a robust version of the Gauss-Newton algorithm to calibrate hydrological parameters. So in this particular case study, which used 3 catchments and 4 models, so it's a relatively modest analysis at this stage, we found that by making some relatively, I would say, moderate changes to the Gauss-Newton algorithm, we're able to outperform these techniques, the SCE, DDS, and the Levenberg-Marquardt, by either match it or improve on it by around 100 times. So we're looking at reductions in calibration costs. So these are the different combinations of models and catchments, and the ratios of improvement. You can see they range from comparable to up to 100 or 1,000 times faster. So it's an initial work at this point. We'd like to very much apply it to more case studies, but if you're interested, something I can also point you to. And finally, if you're interested in these topics, we will be holding a 1-week-long spring school in Spain in May, in Cantabria. So we still have places available, and so if you're interested in coming there for a week, where we go through a lot of the theory and some exercises, you're very welcome to apply, and hopefully we might see you there. Okay, so thank you very much. Hope this was interesting and helpful. I'm here for the rest of the day and tomorrow. So if there are any questions, I'm certainly interested in talking to you. Thank you.
Thanks very much, Dmitri. We have about 5 to 10 minutes for questions. Andrew and John.
Hello, hello. Yeah, thanks very much for the talk. Really interesting. I'd be really interested to know your opinion. In the context of forecasting, how important do you think our lack of knowledge about the precipitation is compared to all of the detailed calibration and structure issues that you talked about?
That's a really interesting question, and we've been looking at the literature and talking to the community about these things. I think that there is a perspective that in forecasting, the main source of uncertainty is the precipitation. But certainly in our work, and again in the work of some of our colleagues, for example, Tom Pagano, I don't know if you know Tom, he has looked at the relative contributions of these things, and he found that, in fact, the post-processing of the streamflow, in many cases, is as influential or more influential than the precipitation quality. So whilst I think it's quite understandable to think that it all hinges on the forecast rainfall, certainly from the empirical results that we're seeing, it's quite important also to describe the uncertainty in the other components of the system. Yep. We were actually tempted to publish a paper on this, but looking at the literature, it seems that it's already been covered to some extent. So I think there's a bit of a disconnect, perhaps, between different sub-communities in the forecasting space. Certainly, I would say that one of the dangers of relying solely on your precip ensembles is that you're not going to get quite the right spread in your streamflow predictions after that. So the streamflow post-processing helps you get that much better. But it's a good question.
Yes, I was very interested in the multiple modeling approaches, which we like very much as well.
Yep.
In that mix, how do you deal with the range of structures within models that might range from conceptual to ones that have more of a physical basis to them, and how do you deal with parameters that may be conceptual or others would be physically identifiable in that whole mixture?
Right, that's a tough one, John. I think that I would say that we have a range of tools there that we have to use quite carefully in this case because we want to avoid over-parameterizing our model. I think the use of cross-validation in space and time is really critical. It's probably the only way that we can establish fairly in as credible way as possible that we're not over-parameterizing. So I think that making sure that we cross-validate is really critical once we start getting into especially distributed models with a lot of parameters. I think the distinction between physical and conceptual models is, I think at times maybe exaggerated. I think that they're all along a continuum.
It's a gradient.
Yeah, it's a range. Yeah. I think being an empirically oriented person in recent years, perhaps, I think the cross-validation is really, really critical. And it provides probably the only relatively objective tool where we can establish that. If we can, if we have a complex theoretically derived model, but it doesn't stand up to cross-validation, I'd probably start questioning it. So I think it's. I don't have an answer to that question. I think that's a fair point. But I think that we are at the stage where we can start to sort of apply these ideas at more and more catchments and learn more about it. At this stage, it's a densely gauged experimental catchment. We had a lot of insight from existing work, so that made it much easier to conduct those experiments. Can we take this and apply this to a new place? At this stage, I think you would need to do a fair bit of setup and analysis.
Yeah. No, it'd be great to engage on some of that. And these are exactly the issues that we're working on.
I think, here. Yes, I don't have the answers to those questions. I'd be very much interested in pursuing them with you guys.
Yeah. Oh, neither do we, so that's good.
Thanks.
I have a question for you.
Yep.
So you've been doing a lot of interesting stuff, looking at uncertainty in your forcing, output, model structure. And of course, this is a multi-query application, so you run your model many times to do this. So here now, in GIWS, we've been working on complex, so-called physically based models, which are very complex, distributed, and might take, 5-6 hours for a single run on a reasonable size catchment. And if we have models running 24 hours or even more. I wonder what's your word of wisdom. I understand the challenges of applying these techniques to those, but what can we do as the community? Because then we are handicapped in looking at uncertainty. So what should we be doing really to handle this?
Well, that's again a really good question, Saman. I think there are multiple lines of attack there potentially. I think one is kind of a brute force way, which would be trying to use parallel computing to try to bring down the wall clock time for these runs to something more manageable. I think inherently, if your model runs in 5 hours rather than millisecond, you're going to be restricted by definition. But I think parallel computing can relieve that to some extent. The second approach is maybe a bit more subtle, and it comes to the choice of computational techniques to use and analysis methods. And in this talk, I presented models that are far simpler to apply than some of the earlier work with hierarchical models and so forth. So, for example, the residual error modeling approach to describing uncertainty, it can be applied with a lot fewer model runs than some of the more complex approaches. So one of the studies that I've had before here, this one here at the top, the least squares method of moments approach. It still has this least squares, the least squares step in the calibration, which might be quite time consuming. But the description of uncertainty is done with the method of moments, which is basically instantaneous. So if you have already invested in calibrating your model, you can describe the uncertainty relatively fast there. So that's the other direction. And I guess here, where I talked about the improvements in optimization speed, again, something that can reduce the total number of runs. So there is a number of angles of attack. Which one is more suitable for a particular case, I think might be case specific. But again, I agree, it's something that is topical. We all would like to model at the highest resolution that we can afford, and so it's a natural question to ask. Yeah.
Thanks very much. That was a very good answer. If there is no burning question, we are just in time. It's already 1. So Dmitri is going to be here this afternoon and tomorrow. If you have interest to meet him, you can let me or Martin Clark know about this, and we'll do our best to accommodate that. So with that, thank you very much, Dmitri, for coming to Saskatoon. I think it has been long overdue, but thanks for coming. It was a great talk, and yeah, we are looking forward to the rest of the discussion over the next couple of days.
Yeah, thank you very much, Simon. Thank you.